So let's think about what we've done here. We have described the trajectory of a mass on a spring. We got it down to this equation of motion, minus kx equals mx double dot. And we showed the solution to that is a sinusoidal function. And sure enough, the motion is sinusoidal motion. This is why it's called simple harmonic motion. It's simple, it's one dimension, it's at one frequency, it's harmonic, that means it moves as a sinusoid, and it oscillates in its motion. But one point I want to make is that this is always the equation for an oscillator. Anything we're describing, if you ever get it in a form like this, you know you have an oscillator. And we won't guess a solution and plug it in every time. Now let's look, the more normal way to write this is to solve for the highest order derivative and write it sort of by itself. So we bring this over here and divide through by the m, and we get plus k over mx equals 0. So if you're ever reading a physics book or doing a physics problem, it might say, show that it's an oscillator. This is all you got to do. If you can show that it's second time derivative or whatever derivative you want, plus a constant times the function itself equals 0, it's an oscillator. In fact, it might be written in a completely different form. It might be y double dot plus a constant times y equals 0. So you might see an advanced physics book. They show that and they say, oh, it's an oscillator. They don't bother to solve it every time. So in physics, we like to find equations that describe many different things. That way we don't have to solve them over and over again. Right? So this is the oscillator equation.